to address our faculty development program. You have accepted. Earlier also, when I was in Geethandale, I conducted AICTE FDP. At that time also, you graced the some sessions. So I am really thankful, sir. Now I request you to continue the session.
Yeah. Thank you, Professor Narasimhulu, for the kind introduction. And actually, it's a pleasure for me to be part of this faculty program. So let me share my screen and then start my presentation. Yeah, I hope the slides are visible.
Yes, sir, it's visible.
Yeah. Right. So within digital image processing, I'm going to talk mainly about fundamentals of image processing and some transform techniques. As I understand, it's the 4th day, so probably some introductory talk is already over. But let me go through some part of the introduction, which may not have been covered. Okay, so why do we need image processing? It's there in multiple fields, but I'm just showing a few examples which are of current interest. For example, you might have heard about Google's self-driving car. So the most important part of self-driving car is, of course, camera, which is on top, right? And it is going to take images, and these images are going to be processed so that it can recognize where the car is going and accordingly change the path, right? And of course, the same thing happens when you have a, let's say, a robo, which has to move. So then it has to see the objects around it and then navigate accordingly. Let me list a few applications of image processing. So processing of images, of course, I think there will be questions at the end, but in case something is very urgent, you can stop me in between. So why do we need to process images and what are we trying to do? So one important aspect is we might want to improve the quality or contrast. This is a very basic fundamental thing. Remove noise and or blur. Blur can be due to so many reasons. For example, there can be motion blur, which is very important in remote sensing. We might want to go further and recognize objects in an image. I mentioned the self-driving car, so this is very important in that context. We might even want to count number of objects in an image. So for example, in a class, instead of taking attendance, I can take a photograph and then count how many students were present, right? These are some of the things we can do. And where do we use them? Where do we use these kind of applications? So in different fields, for example, I mentioned improving the quality of an image or contrast. So that comes under image enhancement. So we want to improve the contrast of images. And why contrast will be low? If suppose we are using not powerful lights, contrast may be low due to poor lighting, as in wildlife photography. In wildlife photography, people take photos at night and there is not much light and the contrast is also poor. So we might want to improve the contrast. Removal of motion, blur or noise, I already mentioned, that's important in remote sensing. Further, we might want to do image classification or object recognition. Finally, image compression. I'm not going to talk about image compression or even classification or recognition. In fact, I will briefly touch upon only the first aspect in this slide. Okay, that itself can be done in multiple ways. So just to give you an example, you see the image on the left, it is pretty dark, right? And we are not able to see very distinctly the faces of these people. Now using image processing, we can convert it to the image on the right. It is not just the brightness which has improved. It is not just a question of increasing the brightness. The contrast has also improved. How do we define contrast? Basically, contrast is when you have a wide range of gray levels. Gray levels are nothing but quantized version of the intensity. So basically, for contrast to be high, you should have dark pixels, as you see here, and also bright pixels like on the face. Whereas in this image, almost everything is dark, right? Okay. Now, some of the fields which use image processing, you can say all fields use nowadays. but to give some specific examples, medical image processing is a very hot field. Remote sensing I mentioned, where satellites take images of the surface of the earth and we might want to recognize what's happening. And actually nowadays we are using in all areas of science and engineering, because you take any field, whether it's biology or engineering, a lot of images are captured and we might want to analyze these images automatically. And the first step in that is to enhance the quality of the image. And even in movies, they are used. Normally in movies, they mention computer graphics, but a lot of it is actually image processing. Now, before we can go into enhancement, let us understand a digital image first. What is a digital image? So suppose I have an object, like on the left, okay, object having some arbitrary shape, and then light is incident on it in a certain direction. Now that light is reflected, and then it goes and is incident on an imaging system like a camera, and then inside the camera you have an image. So this is the object on the left, and then the image on the right is formed inside the imaging system. I think I request participants to mute. Unless you want to speak something specifically, you can unmute, but otherwise there will be a lot of background disturbance which will disturb everybody. Plus, please mute unless if you want to talk, you can please unmute at that point. Okay. So this is the image. Now you can see that if you look at the object, there is a continuous variation in intensity, which is true for the image as well. But this is not a digital image. You can call it an analog image. Okay, but if you digitize this, actually that happens in any digital camera. It happens automatically because you will have sensors or imaging elements within this, and then they will digitize it, convert from analog to digital, and then the digitized output is what you see on the extreme right. So how is this the digitization done? Basically, the imaging system, the digital camera, you can say, samples the image at regular intervals. Okay, there is periodic sampling of the intensity values, and each imaging element occupies a certain region, right? So throughout that region, which is called as a pixel, so the small square is a pixel, it will be same intensity. Essentially, what you're doing is it is sampling at a single point or spread over a certain region, and what you're getting is the average intensity in that region. So now the difference between the analog and the digital image is clear. In analog image, you have a continuous variation in intensity, whereas in a digital image, you have sudden variations, right? Now this will be more obvious in the next few slides. Same example I'm taking just to show the effect of digitization. So you have this on the top left, you have this continuous image, and then let's say I'm looking at various points along this line AB, and then I'm sampling the intensity at various intervals. So first I'm showing the intensity variation along AB. Now initially it's white, right? Very bright. So that's why it's high value of intensity. Then suddenly it decreases when it cuts across the edge of this object. Then again it starts rising. You can see that there's a variation in intensity within this object as you move from A to B. So that is what is shown, and this random variation is basically noise. Okay, you can see some random variation superimposed on the variation which is present. So this is due to noise in the imaging system. Fine, and then you have reached B at this point. Now sampling is shown here. You are sampling at specific points and capturing the intensity at those points, and further you are quantizing. So there are two effects involved here. One is sampling, right? Sampling means you are measuring the intensity at specific locations which are periodically spaced. But further, there is a minimum intensity and maximum intensity. In the original object, the intensity varies continuously from low to high. But once it is quantized, it can vary only in steps. For example, here, you see that there are 8 levels. Normally, this number of levels will be a power of 2, because we are going to use bits to store the intensity values. So therefore, the number of levels will be a power of 2. And most digital images are 8-bit images. That means for each pixel, we will use 8 bits. That means the intensity can vary from 0 to 2 power 8. Okay, minus 1, because the maximum will be 255 when all bits are 1. So the minimum is 0 and maximum is 255. In this case, of course, only 8 levels are shown, but normal digital images, the number of levels is 256 levels, from 0 up to 255. Then you can see that this final image on the right bottom is the quantized and sampled image. So both effects are seen here. There is a discretization in the spatial domain, which is sampling, and in terms of intensity also there is discretization, which is what is known as quantization. Okay, some of these things I don't know which part has been covered, so let's move ahead. So just to show that same thing again, contrast between the original image and you have this digital image on the right, and the smallest square which you see here is 1 pixel, or picture element, pixel for short. Okay, now what is we want, remember, when you think of images, you should think of them as, instead of looking at it as an image, you can think of them as an array of numbers. Okay, if it's a grayscale image, it's a 2D array where each pixel corresponding, there is a number, simply a number which varies from 0 to 255 for each pixel, right? So I will have an array, 2D array for a what is called grayscale image. In real life, we call that a black and white image. But in image processing, we call that a grayscale image. There are different shades of gray. Okay, so we need a 2D array of numbers to represent the image. So you think of each thing as a 2D array or a matrix. That's all. An image is nothing but a matrix filled with numbers which vary from 0 to 255. And if it's a color image, it is going to be a 3-dimensional array where there are 3 layers, one for the red, one for the green, and one for the blue. And there is a spatial coordinate, right? I want to refer to a point within the image. Normally we use X and Y coordinates. Now the convention used in image processing is different from the convention used normally in mathematics. In mathematics, we take origin at the, let's say, the bottom left, and then y-axis goes upwards and x-axis goes horizontally, right? But in image processing, what we do is we take the origin at the top left here, as shown in the image. This is the origin, and y-axis, what is normally called y, of course, this is just a convention, but you take it along the horizontal direction, and x is taken vertically downwards. Now, the reason for doing this is this exactly matches with the convention used for matrices, because we know that when I want to refer to a matrix element, right? Let's say this matrix is called A. Then to refer to a particular element, I have to tell the row number. Row number is simply now my x coordinate, and column number is my y coordinate. Okay, so that's why we are using this convention. So element will be referred to as A brackets x comma y. That's how we refer to it. So this is how we store it on the computer also. It's stored as a 2-dimensional array. Let me give an example of that. So for example, let's say the image looks like this. So what is this image? It's very simple. Ignore the white region and the surrounding. Okay, that's not the image. The image is just this rectangle, which is mostly black, but with this white strip in between. This is just 1 pixel bit wide. Okay, and in fact, you cannot judge it is 255 or something, but actually it is 128. It's not fully bright. It's 128, and this black region is of course 0. So now if you read this image, so when I say read the image is stored in your computer, and since I think this workshop you are using MATLAB, I'll come to the MATLAB command. There is a command called imread or image read, which will simply read this, and then it will, in your memory, it will upload all the numbers. So what will it upload is this. So the image you can see has basically it has 9 columns and 3, 4, 5, 6, 7, 8, 9. 9 rows and 9 columns. So it's a square image. where except for the middle column, which is 128, everything else is 0. Is there a question or here's some sound? Okay, let me go ahead. So this is what it is. Now let us look at the, I mentioned sampling and quantization. Let us see what happens when you do sampling. So what we are seeing here, just move it. Yeah, we can move it like this. So basically the image on the top left is a 124 by 124. So many pixels, it's an 8-bit image. Okay. Now, what is this? It is 512 by 512, which means I have reduced the number of pixels. How do I do that? Basically, you can do it in various ways. And then, of course, size is same. So what has happened is, it's a 512 by 512 image, but to get the same size, I have increased it. Okay, by simply duplicating some rows and columns. Okay, not much change, you might say. But if you go on doing this, finally, you will reach 32 by 32, which is in the bottom right. 32 by 32 pixels, but resampled into the 1024 by 1024. You can see the effect of the this is effect of sampling, not quantization. Okay, you have reduced the number of pixels, and therefore this is called pixelation. Now, similarly, you can do for look at the effect of quantization. Yeah, this is the effect of quantization. So here I have a 256. The top left is a 256 level image. That means the intensity varies from 0 to 255. So you can see a lot of nice even variation, but I go on reducing the number of levels. Okay. So from 256, maybe I make it 128. So this is 128. Then I reduce it further to 64 and then 32. So what you can see is that the number of levels is reduced. So how you can do this is very simple. For example, to reduce by a factor of half, from 256 level to 128 levels. What you can do is 0 to 1 can be replaced by 0. 2 to 3, 2 or 3 can be replaced by 1 and so on, right? You are merging 2 levels to 1 level. Then that you can keep on repeating that process. Now you can see here there is something called false contouring. What is meant by false contouring is that in the original image, it looks like a gradual variation in intensity. But due to this decrease in the number of levels, the intensity is changing very suddenly, correct? And that is why you have this false contouring. False contouring means it appears that there is a sudden change in intensity, which is not true. Actually, it's a gradual variation. And in fact, in any digital image, there is only a sudden variation. But with more number of levels, that effect is less. But if you go to less number of effects, the effect is very obvious, sudden jump. Now, in fact, if you go on doing this until you reach 2 levels, that is this last image, it's called a binary image. Grayscale image means more than 2 levels. Binary image means only 2 levels, 0 or 1. So you can see that you are having only 2 levels here. Fine. And in fact, the false contouring is very visible in this image at the top right. You can see all these variations, just as there are layers on layers. But actually, it's not a sudden variation, it's a gradual variation. Okay, so this is the effect of, we talked about sampling and quantization. Now, let me give you an overall view where we are going, why we need to do this. As I mentioned some sophisticated applications in the beginning, like robo and so on, but that involves a lot of steps. What are the steps? For example, it will start with image capture, then digitization, then loading the intensity onto a computer because we want to do the processing in the computer, right? Noise reduction is the first step. Because if there is noise, any other recognition algorithm is going to get confused. So first you reduce the noise by doing some kind of filtering. Then you might want to do image restoration. Okay. Actually, these two things can be clubbed. Image restoration can include noise reduction. Then image enhancement to increase the contrast. Then segmentation. So the last 3 parts are where the recognition aspect comes in. Segmentation means dividing the image into various regions according to the number of objects present. You might go for a simplified representation of image. And finally, you recognize the object by comparing with the template. Now, in these different steps, I am not going to discuss about all of these. There is no time within 2 hours. That is what image processing is all about. But I will concentrate on image enhancement and noise reduction and so on. Okay, only this middle part I will talk about. We already mentioned about digitization, and this we will see. But mainly I will concentrate on noise reduction, image enhancement. Okay, let me go into that aspect. Sorry. Yeah. So I mentioned about noise reduction by filtering. It can be done in 2 ways. One is called spatial domain filtering, and the other is called Fourier domain filtering. Right? So I will cover both aspects one by one. First, we'll go to spatial domain filtering, which is easier to understand, and then we'll go to Fourier domain. And especially in Fourier domain, students have a lot of confusion with respect to understanding what is a Fourier domain. So when we come to that, I'll mention the usual confusion which happens. Let's start with filtering in the spatial domain, which is very easy to understand. For example, the simplest operation is mathematical operation is averaging. That's an example of filtering in the spatial domain. So we simply take a group of pixels within what is called a mask and replace the center of the mask by the average value. What we do in averaging is we choose a mask of size m cross n. These numbers are usually small. M and n are small. In fact, you can typically we choose a square mask. Here I have taken m and n, but normally we can take a square mask like 3 cross 3. That means 9 pixels. So imagine the mask to be placed on starting from one corner of the image. That means, of course, one problem which will come here is if I take the, let's say the pixel at the top left corner and place the 3 by 3 mask with the center of the mask here, some part of the mask will go out. So what do we do about these pixels which are outside the mask? Sorry. So there are multiple ways of tackling this problem. So one way can be that you can say that simply ignore so you can say that you will simply ignore the pixels at the sides. But the other option which is usually used is that you go for what is called padding. That is, you put some extra pixels on all sides. Then what do? We replace the current value of the gray level at the center of the mask by the average gray level of all the pixels in the mask. So this is a very simple operation, right? But remember, it has to be done throughout the image. Starting from one corner. So we will take average of 9 values, replace that pixel, go to the next, shift the mask by 1 pixel, then again repeat the operation, so on. So what happens is if you do this filtering in the spatial domain, the computation required is quite enormous. In fact, that is why we go to Fourier domain. In Fourier domain, the computation required is much less. I will not prove that, okay, because there is no time, but that is why we go to Fourier domain. And why do we do this averaging? It can be shown that it will reduce noise. Basically, noise gets wiped out. We'll see that, why noise gets wiped out. Just to show some example. So this is an example of averaging. Let me, yeah. So the mask sizes are mentioned here. This is the original image in the top left corner. Then what you do is, you take a mask of size 5 cross 5. Okay. or 15 cross 15, 30 cross 30, and so on. Okay, 1 second. This is actually 1 second. Low pass filtering. 1 second. 1 second. I think the slides have got mixed up. Let me. This has got mixed up. It has come from Fourier domain. I'll go to averaging. Yeah, this is the result of averaging. That actually came from low pass filtering, which I'll talk about later. Okay, result of averaging smoothing is shown here. Okay, this is better. So you have mass size. This is the original image. Then you apply on this 3 cross 3. That is the next image shown, right? No difference, almost no difference. But then you go on increasing the size of the mass. This is 5 cross 5, 9 cross 9, 15 cross 15, 35 cross 30. So what you see is that as the mass size becomes bigger and bigger, there is some blurring. Correct? In fact, the blurring is most obviously seen if you look at these rectangles which are here, these dark rectangles which are here. As the mass size increases, it is getting rounded off, right? You can see that. Basically, the edges, what is happening is the edges are getting blurred. Actually, why I showed that previous image, which is previous slide, is for low pass filter. Averaging is essentially like a low pass filter. Okay, we can easily show that. It's like a low pass filter. Now, what does a low pass filter do? It will allow low frequencies and not allow, it will pass the low frequencies and cut off high frequencies. Now, this, if you see this rectangle, dark rectangle, which is here, and the background is brighter. So there is a sudden variation at the edge, which means that corresponds to basically a high frequency component in the image. Okay. So therefore, when you apply averaging, which is like a low pass filter, it removes high frequency, and therefore the sudden variation is not there in the subsequent images. Fine. This is the explanation for averaging. Another intuitive way of understanding is take, for example, this region where there is basically it looks like noise, right? This region over here, and you have these black dots. Now, suppose I have a black dot, and then surrounding that is a white region. I do averaging. Essentially, the black dot will almost disappear because it will be replaced by a much larger value, which is the average of all the pixels within the mask, right? And so this is what is called smoothing. So essentially, what is smoothing? It increases the dark value of dark pixels and reduces the value of bright pixels if they are surrounded by the other values. So maxima are brought down and minimum intensities are brought up. So therefore, as mass size increases, the effect of smoothing is greater. That's what we observe from here. Okay. Let me move ahead. But sometimes this blurring of edges which happens can be done deliberately. Why it will be done deliberately? Suppose I want a simple representation of a complex image. What is a complex image? Take the image on the left. Okay. So it has a lot of objects, right? This is actually a picture of the night sky taken through a telescope. So there are a lot of stars, galaxies, whatever. So many objects are there of different sizes. There are small bright spots which are there, and then there are bigger objects. Now let's say I'm interested only in the bigger objects. That means I want to count only the bigger objects. Let's say I have a counting algorithm, but the counting algorithm is going to get confused by the smaller objects. It should not count the smaller object, right? So the best thing is to do is to simply wipe them out. How to wipe them out? You can use an averaging mask. Okay, there are further operations which are done here called the thresholding, which I will not go into. First, when you do averaging, it gets blurred. Then you do thresholding. Thresholding can be understood simply like this. Beyond a certain level, that means if it's above 128, suppose you want to threshold to 2 levels. Above 128, make it 255. Below 128, make it 0. Then you get this image on the right. Okay. Now you can easily count. In fact, most counting operations operate on counting algorithms, operate on this binary images. They don't operate on the original image because it's very complicated. So this is how you can use averaging to get a simple representation of a complex image. Okay, one more. Averaging is just one type of filter in the spatial domain, but you can have various filters. You can of course do filtering in the Fourier domain, but even within spatial domain, you can have different kind of filters. What are those? You can do simple averaging. In fact, whatever I mentioned till now is simple averaging. But you can also do what is called weighted averaging. That means all pixels within the mask don't have the same weight. For example, the center pixel may get more weight. That is called weighted averaging. I will not discuss that. Instead, I'm going to discuss something called median filter. So median filter comes under the class of statistics, order statistics filters. Okay, what do we do in median filter is replace the gray level in the center of the mask by the median of all the gray values in the mask. What is median? Median is basically middle value, right? So for median filter to be applied, you simply arrange. I mentioned about, let's say the median filter is 3 cross 3. Then you arrange all the 9 values in, let's say, ascending order or descending order, doesn't matter. Pick the 5th value. So replace by that. Now, this is actually in some ways superior to the averaging mask. That is what is shown here. Okay. So you see here that, let me see whether I can, no, I can't shift it out. Okay. See, the image on the left is corrupted by noise. You can see that there are black dots and white dots. So this is called salt and pepper noise, because it's like white dots are like salt, black dots are like pepper. So this is called salt and pepper noise. And I want to remove this because I want to have a nice image of this. It's basically some circuit board, right? Integrated circuit board. So how to do that? Suppose I apply averaging. As I said, averaging will remove noise. But if I do averaging, what happens? The noise is not completely eliminated. It's reduced, of course, because the very bright white dot will now become less bright and the dark dot will increase. But it's still not completely removed. But if you apply median, it's completely gone. And you see, it's a nice picture on the right. So median filter is ideal for salt and pepper noise. Okay, why is it completely removed? You can easily understand. Suppose I have a pepper noise. Pepper noise means what? A 0. I have a pixel with 0. And let's say all the surrounding are not 0, non-zero values. Then if you arrange in ascending order, obviously the output will be non-zero. Okay, and a much higher value. You can take an example. Okay, let's say I have 0 surrounded by all 255. If I take median value, what will be the median value? It will be 255, correct? Because out of the 9 values, 8 values are 255, 1 is 0. So 0 will be replaced by 255. 0 is the center of the mask. So 0 is replaced by 255. But if I do averaging, what will happen? I will get 8 values are 255. So I will get 8 into 255 by 9. So I will not get 255. Okay. So therefore, there is some residual effect of the noise if I do averaging. Whereas if I take median filter, it completely removes the salt and pepper noise. So median filter is very nice for salt and pepper noise. But exactly this aspect also can cause a problem, as I will mention. I will now mention what is the problem with 3x3 median filter. So this is I'm just summarizing what I said. So if you are using a 3 cross 3 median filter, arrange the 9 gray levels which fall within the filter in ascending, descending order. Now for the sorting, etc., MATLAB has an inbuilt command. So what you have to do is, of course, the 9 values within the mask have to be arranged in a separate array, a 1D array. And then you will have to apply the sort command and then take the 5th value in that 1D array. That is what you have to do. But for these inbuilt commands are there for sorting. You can use the MATLAB command for sorting the numbers and then picking the 5th value. Choose the 5th value in the list of the array. This is by definition the median of the 9 numbers. Right? And as I mentioned, median filter is very good at eliminating salt and pepper noise, also called impulse noise. And it does not lead to blurring of edges as much as simple averaging filters. That was obvious from the previous slide, right? Let's go back. You see here that the edges are not blurred. Extreme right image. edges are not blurred. Whereas in the middle image, the edges are blurred. It's not a very sharp image. That's because you are doing averaging here in the middle image. Last image, you are doing median. So, yeah. So, advantage of median filters does not lead to blurring of edges as much as simple averaging filters. Now, let's look at some MATLAB commands which will be used for image processing, because it is no use just learning the theory, right? We want to try hands-on. I am sure there are some lab sessions, and in 2 hours I cannot deal with everything, both the theory and I will concentrate on the theoretical aspect. But I will mention, this is a good place for mentioning about some MATLAB commands for image processing. As we know, the first step is to read the image. So there is a command called imread, and MATLAB has very good help features. So if you want to know the syntax of a command, you just type help followed by imread, and it will give you it will give an example also. So what does this command do? Basically, it calls, this is an inbuilt function. Basically, it's a MATLAB function. imread is a MATLAB function which will operate on an image. Actually, this format need not be mentioned. Suppose I have a JPEG image. Okay, so file name .jpeg. This format need not be given. You can give or you need not give, optional. If you do that, it reads the image and stores the values, that is intensity values, in a 2D array called A. And of course, if it's a color image, then it will be a 3-dimensional array. A will become 3-dimensional. And you can use the size command. MATLAB has a size command, size. Size. If you say size of A, it will return number of rows and number of columns. And if it returns 3, that means it's a RGB. Size command will also tell you it's a 2D image or a grayscale image or color image. And at the end, in this A, pixel values are stored as unsigned 8-bit integers. Okay, that is a format of the data which you have now. But for mathematical operations, this is not enough. You want to do any multiplication, any operation on A, you have to convert to double precision. Okay, there is a double command which will do that. So as I mentioned, for a grayscale image, the array will be 2-dimensional, whereas a color image will be stored as a 3-dimensional array. And you can also convert a RGB or color image to grayscale using this command. RGB to gray of A means, if A, first you read the color image, right, and store it in A, then RGB to gray means it will convert the RGB image or color image into grayscale image. So you are actually losing information here. But for some algorithms, maybe color is not important, then you can use this. If color don't require the color information, it makes things simpler, then you convert an RGB image to a grayscale image. Yeah, as I mentioned, if you want to do any mathematical operation on the array values, which are the pixel values, you have to convert them to double precision, use the double command. You can also store the output. I mean, if you want to keep the original thing, then you can say B is equal to double of A. Then original array will be preserved, and then a new array is created called B, which will have the double precision values. Here I am overwriting the array. Same array is used for both the things. So this converts elements of array A to double precision. And this should be used before applying any mathematical operation like multiplication and division on elements of array. Because for any, we will see that there are many transformations which will do where it requires to be in double precision. Therefore, this imread followed by double is almost there in every program. Every operation you do, these things will be there, followed by other relevant operations. And after doing all these operations, you want to store it back as an image. Then imwrite is the opposite of imread. So imwrite will write the array B. Let's say after doing all these operations, it becomes array B. Then array B can be stored as a file, output file name .fmt is for format. Format you don't have to give here. You can tell JPEG, or you don't have to tell and close the bracket here itself. MATLAB will understand even if you don't specify the format, because the file extension will have that, whether it's JPEG or BMP or whatever it is. So this imwrite command stores elements of array B as an image file. Then you can, so it's a modified image now. But one thing is there that remember you converted it to double precision. So before writing it as an image file, you have to convert it back to unsigned 8-bit integer. So B is before actually this command uint 8 of B. This last command should come before IMWrite. Before using IMWrite, I'm converting B into a unsigned 8-bit integer. That's the meaning of this. Okay, this is the meaning. Okay. Now, what are the issues? I mentioned that till now, whatever I said, it looks like median filter is very advantageous. But there are some problems with this median filter. What are that? What are the problems? Okay. So remember that when we're talking about salt and pepper noise, we said that small spots like black dots or white dots will be completely removed. But suppose it's a genuine feature, that small feature, if it's a genuine feature, that is also wiped out. So whether it is noise or genuine feature, both are gone, right? That's the issue with median filter. One thing is, of course, computationally intensive. Why computationally intensive? Because remember, sorting is involved, and sorting can take a lot of time. And before sorting, you have to first of all bring out those, store those values separately within the mask, right? So that is also an assignment operation. Further, you are doing sorting. So it is computationally intensive, and further it will remove small features like thin lines and points. As I mentioned, it removes salt and pepper noise, but it will also remove thin lines. I will show an example. And one more not so obvious thing is that it shifts, even edges are shifted, which are not straight. I'll show an example. So for example, look at this. Let's say part of the image looks like this. Let's say my mask is 4x4 median filter. Okay. So within that 16 pixels within the mask, I have a row. Basically, this is a line which is having 255. So this is like a bright line on a dark background. But if I take the median value out of the 16 values, the median value will be 0. So in fact, every 255 will be replaced by 0. So this line is completely wiped out. So thin lines are wiped out. And in fact, the thin lines may be carrying some important information, especially in medical image processing, etc. This can be very serious, right? We don't want to wipe out some genuine feature. So this you should be, there are ways of getting around this as an issue. And I talked about shifting of edges, that is shown here. See here. So this is there. Okay. So you see here that there is an edge which is not straight, right? Going like this at an angle, diagonal, and then coming down like this. So this is an edge basically, because edge between 255 and 0. Now what happens to this when you apply, let's say I'm applying 3 by 3 now. Okay. Then this 255 will be replaced by 0. So the nature of the edge will get changed. Okay. Right. So we can modify because of the two problems which I mentioned in the previous slide, we can modify the median filter mask to overcome this defect. So how do we modify? Let's say it's 3x3. I want 9 pixels within the mask, but those 9 pixels need not be forming a square. Okay, I can take like this. So this is, okay, what is this? This is actually the mask I'm going to use. Meaning of this is not the pixel value. The meaning of the 0 is that I am not looking at the value of this. So what I have done is I am taking a 5x5 mask. Now, but wherever there is a 0, that means that value of the pixel is not considered. And wherever there is a 1, it's considered. So you can see that there are 5 ones here and 4 ones. So 9 ones are there. So it's like a 3 by 3 mask. But only thing is the pixels I am considering are in the shape of a cross. So what will happen now? If there is a thin line, all these are having value 1. So the thin line is considered. So both horizontal and vertical lines will not be wiped out by this procedure. Okay, is that clear? So this will preserve horizontal and vertical lines of 1 pixel thickness. But of course, if the line is diagonal, it won't preserve. Then you'll have to go for a different type of mask. You'll have to think of some other mask. Now let me just look at the time factor. Yeah, because I want to check how much time we are going good. Okay, so we are going at a good pace. And as I said, if there is some doubt, you can stop me in between. Otherwise, at the end, of course, you can ask me questions. Okay, now let's look at techniques for improving contrast. Till now, we are looking at removing noise. Okay, we did averaging, and then we looked at median filter. All these are to remove noise. But let's say I want to improve contrast. What do I do? Okay. What I do is there are multiple techniques for that. One is called applying a gray level transformation. You can also look at what is called histogram processing, and then you can look at spatial domain filters, right? So whatever I told you so far, averaging, etc., doesn't it actually reduce the contrast because it leads to blurring. Remember, so that's like reducing contrast. So we have to do the opposite of averaging. That will come under the spatial domain filter. But let's first look at maybe gray level transformations. Yeah. So all the possible gray level transformations are summarized. What do we do in gray level transformation? What we do is we simply think of a mathematical transformation of this form. This equation which you see here, S is equal to C R power gamma. Let me explain the symbols. R is the input gray level. Input gray level means gray level of the input image. Now remember, input image varies from 0 to L minus 1. What is L? L is some 2 power n or power of 2. So for example, in our case, 8-bit image means L is 256. So the intensity varies from 0 to 255. So this is the input gray level. Now what I want to do is, I want to map each input gray level to some output gray level. Some kind of mapping I want to do. That is what this is doing. But here, I can do different things by choosing this exponent gamma. So for example, if gamma is equal to 1, that is simply a straight line. I'm not doing anything. And remember, this constant C is chosen such that 0 is mapped to 0. That of course is straight away obvious from here. If I put R is equal to 0, S is 0. But 255 should get mapped to 255 because I don't want to increase the number of levels. So C is calculated. I won't go into the calculation. You can calculate C. All you have to do is put R is equal to 255 and whatever be gamma, you choose that gamma, and S is also should be equal to 255. So from this equation, you can determine what should be the value of C. Okay, and obviously C depends on gamma. The value of C depends on the gamma you are choosing. And coming back to where we were, so as I said, if gamma is equal to 1, it is this. Okay, and if you have a gamma which is greater than 1, okay, that is the nth power. So as you go on increasing the power, the curvature of the transformation increases. Okay, so this straight line which is there is gamma is equal to 1, and if you increase gamma, it will become like this. Increase it further, it becomes steeper. Now what is happening here? So let's look at this. What is happening here is that one second, I need some help. Is there any way of removing this? I don't know whether this is coming on the screen. I don't know how to remove this.
Which one, sir?
No, this. Are you seeing this? Is the entire slide visible or something is there in the bottom?
No, sir. Entire screen is visible.
Entire screen is visible, sir.
Okay, no problem. Okay. I am seeing. Okay.
Go ahead.
Fine. Okay. Yeah. Then this, if you increase the power, this gamma is the power. If you increase the power, it becomes steeper and steeper. What is happening here is that if you see, for example, you take this nth power, and let's say the middle is here, right? L by 2. So in our case, L by 2 will be 128. So 0 to 128, okay, is mapped to what is happening. So 128 is mapped to a very low value, correct? Because of this curvature. So that means if most of the pixels are bright, let's say I have a very bright image, what happens? Most of the pixels will be in the range 128 to 256. But these are now mapped to 128 is mapped to a very low value. So basically you are stretching the range. The range that is called usually dynamic range. Dynamic range means the range is 0 to 255, but you are looking at dynamic range, means what range is actually present in the image. So that in our case is usually less. If it is 128 to 256, only 128 levels are present, but that is being stretched because now 255 is mapped to 255, but 128 is mapped to a very low value. Maybe this is something like 32 or something. So the range has now become 32 to 255. So if you have a very bright image and you want to, bright image means it's going from 128 to 255, but the contrast is low because all the pixels are bright, contrast is low. So this will increase the contrast. So if you have a bright image, you should go for gamma greater than 1. And if you have a dark image, you should go for gamma less than 1. Just the reverse effect. What is the reverse effect? If you have a dark image, most of the pixels are in the range, let's say 0 to 128. Now, if you have gamma less than 1, basically 128 is going to be mapped to, this is some 192 or something. So the lower range is getting stretched. Okay, in fact, you can go for even log transformation. An inverse log is basically exponential. So if you have to summarize this slide, if you have a bright image, then go for gamma greater than 1 to improve the contrast. And if you have a dark image, then you go for gamma less than 1. This is a simple idea, and of course C has to be calculated depending on what gamma you are choosing. Okay. Now that is one simple idea. In fact, you can even automate this process. Okay, there are simple algorithms where it will look at the image and then identify whether it's a bright image or dark image and accordingly choose gamma. You can even write a program which will do this. It is not that manually for each image you have to select gamma. You can even automate this entire process. It's possible. Okay. Fine. Now let's move ahead and look at histogram processing. What is histogram processing? Histogram, within histogram processing, I will discuss histogram equalization. What we want to do is convert a low contrast image to a high contrast image by manipulating the histogram. Manipulating the histogram means changing the histogram. Now, what kind of histogram corresponds to high contrast? Basically, what is called an equal histogram, because I want all pixel values to have same probability, correct? I should have dark pixels. I should also have bright pixels, which means histogram should be flat. I want a uniform. It's usually called a uniform histogram, like this. Okay. Now let's look at this image. This is now a low contrast image, because what is happening is most of the pixels are here. What is histogram? On the y-axis, you have number of pixels. X-axis, you have pixel value, which is going from 0 to 255. And on the y-axis, you have the number of pixels which have that particular value. For example, if it's 128, this tells you that most of the pixels here in this image are having 128. That's why this big peak is there. And how to obtain this? In MATLAB, there is a simple command called hist, H-I-S-T, which will simply generate the histogram. Okay, you don't have to write a big program to do this. Hist of A will simply give you the histogram. Fine. Yeah, it will do that. And you see that our input image has a very poor contrast because the histogram is not flat. In fact, it's sharply peaked. But I want to spread it out. How to spread it out? That's the question. Okay. So high contrast, I want to change it like this. I want to change it to something like this. So you have you see the contrast obviously is more here at the image at the bottom, and the histogram is also almost flat. So I want to convert this histogram to this histogram. How to do that? It's not very difficult. Okay. So the histogram equalization procedure is very simple. I will tell you the formula, then just take 2 minutes to prove it. What you do is you have to do a transformation on the input gray level R. What transformation you do? First of all, this is nothing but the cumulative probability. By probability here we mean, what is probability? It is nothing but the frequency of occurrence of a certain gray level, right? So what we do is take let's say there are totally, the gray levels go from 0 to k. So count, the histogram will basically tell you number of pixels which are having a gray level j. So take nj, divide it by n. N is the total number of pixels in the image. Basically, this is nothing but probability. Out of the total pixels, how many pixels are having a certain value? So this is probability. Then I have to add this. This is nothing but cumulative probability, what we call cumulative probability. So the output pixel value is simply the cumulative probability. But then this will, remember, the cumulative probability can be at most 1, but I want a gray value 255. So simply multiply this by 255. But then this may not be an integer, right? But the gray level, output gray level has to be an integer. So what you do is multiply this by 255 and round it off. Now, where did this formula come from? I'll quickly tell you. Okay, it's easy to understand how this formula comes. So basically, we are looking for a mapping or a transformation from the input gray level R to the output gray level S. So we want to do a one-to-one mapping. Okay, if it's a one-to-one mapping from R to S, and I have some distribution of the input gray levels, right? P of R is the probability of the, let's say, a certain gray level. And for mathematical convenience, first we take R to be varying from 0 to 1. Then you can simply multiply by 255. Okay. What is this quantity on the left? P of R dr is the probability of R. Okay. P of R, remember, is probability density. I multiply by dr, which is a small range in R. So this is probability. Probability into total number of pixels n is number of pixels which have a small range dr, from R to dr. And all those pixels are getting mapped to a small range in S. These two must be equal because the number of pixels is conserved, right? So that's where this comes from. Then I integrate both sides. But remember that P of S is simply 1 for all because it's a uniform histogram. Then I will get integral ds, and integral ds is simply okay. So that's what I have done. I have cancelled n on both sides. It was written anyway for understanding. And then what I have done is I have put P of S equal to 1 because I want a uniform histogram, right? P of S is 1 for all values of S. So it is simply ds. Then integrate both sides. To integrate both sides, this is what you get. I integrate from 0 to R for the input image and 0 to S because R gets mapped to S and 0 gets mapped to 0. And the discrete version of this is that summation. Okay, integration means summation, right? So that's how you get that. In the discrete version, P of Rj is Nj by N. We are dealing with discrete version only because it's a digital image. And the integral is replaced by summation. So that's how we get this formula. Okay, let's go ahead. But this histogram equalization, even though it looks so simple, it usually doesn't achieve the purpose. Okay, one second, let me show. Okay, I'll come back to this. Yeah, see, look at this. I'll go back to the previous next slide because that's a different technique. The output of histogram equalization. Okay, so what you are seeing here is, you can see here the input histogram is like this. It's a very bright image. Okay, and I wanted to get uniform histogram, but I did not get. In fact, this. Note the washed out appearance. Contrast is not high. It simply become brighter. Why is that happening? That is happening because, first of all, this cumulative probability is an increasing function. That's what is shown here. Okay, the transformation is always a monotonically increasing because you are going on adding probabilities, right? And one more thing is you are also doing rounding off. So due to that, what is happening is that it is developing this washed out appearance. So we need a better technique. So histogram equalization is not achieving the purpose. And though in theory, if it's a continuous function, you will get it. But it's not a continuous function, right? It's a digital image. So what do we do in that case? So that's where histogram specification comes in. So the same image, input image I'm taking, what I'll do in this case is I'm going to specify the histogram I want. Specify means you will say, okay, I will specify the uniform histogram, but no, then you will get the same problem. What we do is usually you're not, see, basically in the previous case, problem happened because I was very greedy. I wanted completely flat histogram, right? So what I'll do now is I don't aim for that. I will aim for a histogram which is like the original image but slightly better, like here. Yeah. So compare these two. So I have the input histogram P of R versus R. Then the output histogram is like this. Okay. You notice the difference? It's like it looks exactly same except that I'm trying to spread it out a little bit more. Instead of making it perfectly flat, I try to spread it out a little bit. So how do we do this? What you have to do is map the areas. That is this dotted line, take this area, and then we are asking the question, and the area under the curve is simply the integral, right? And discrete version is a summation. That's how you get this. So we go on varying Z. Now we don't know what is the Z corresponding to R. That's the mapping we want. So we go on varying Z until this area under the curve becomes equal to this area. That's what this relation means. Basically, we are equating the area under the curve. So for each value of R, you'll have to do it, go on varying Z till it matches. So this program will run in a loop. You go on changing Z till this summation is greater than the original summation. Okay? This is area under the curve. So that is this on the right. And then this should be, that is a summation over Z should be greater than that. That's what we are, is histogram. This is called histogram specification. I am specifying the histogram I want. And specified histogram is usually not the equal histogram, but slightly better than the original histogram. Yeah. So usually the results of histogram specification are better. Now, finally, I want to take up the last spatial domain operation. We want to sharpen images. And remember that when we did averaging, it was blurring, right? So I want to do the opposite. Remember, in averaging, you are adding up values within the mask. So for that will lead to blurring. Now you want to sharpen images, you have to do the opposite, which means take differences. And differences are like derivatives. So usually what is done is there are two derivatives possible, first derivative or second derivative. And in the two-dimensional image is two-dimensional. So the second derivative is also actually called a Laplacian. The first derivative is called the gradient. So I will just look at second derivative. Okay. So this is the definition of Laplacian. You take the second derivative. Now f here is the intensity value. Okay. See, this is given for just your understanding. This partial derivative, it is just given for understanding. It is not that we are actually going to implement this, because remember, f is the intensity values in the image, which is not a continuous function. There is nothing to differentiate here in the usual sense of calculus. But what we will do is, how do we calculate second derivative? I'm not going through the proof of this. Basically, it's the differences, right? So, and the minimum difference you can do is 1 pixel apart. So that's how you get this. I think I'll not, since there is lack of time. If there is some doubt at the end, we can come back to this, how we get this. But essentially, it's like taking difference between successive pixels. That will give you this. Okay. So, and because the main thing you have to understand here is because the Laplacian is a derivative operator, its use highlights gray level discontinuities. That means it increases the discontinuities in image and de-emphasizes regions with slowly varying gray level. Actually, you can easily see from this formula what we are doing. You are taking a pixel which is at x comma y. F of x comma y is the center of the mask, intensity at the center of the mask. Then you are having x plus 1. That means 1 pixel below, x minus 1, 1 pixel above. Y minus 1 means 1 pixel to the left. Y plus 1 means 1 pixel to the right. Add all of them. Subtract 4 times the center pixel. If all pixels are same value, this will become 0, correct? But if the values are different, there will be a non-zero value. So the Laplacian, what it does is wherever the intensity is uniform, it will give 0 output. And wherever there is a variation, that variation will become more because of this multiplying by 4. And various types of Laplacians are possible. Just showing it here. You can. This is the mask for that whatever I showed you expression in the previous thing. So what you are doing is minus 4 times f of xy, correct? So take the central pixel, multiply by minus 4. Take the pixel on the top, bottom, left, right. So add everything, and wherever it is 0, that means I'm not using those values. You can also have the opposite of that, which means center pixel is multiplied by plus 4 and not minus 4. But in that case, the remaining pixels are becoming minus 1. You can also have variation where you involve the diagonal pixels as well. This is also possible. It's also called a Laplacian, even though this is not the based on that expression which we got. Just to show the application of Laplacian. So wherever it's uniform intensity, remember it will disappear and only the edge will become more prominent. It will become more prominent now. And what you do is, of course, here the most of the moon has disappeared. So add it to the original image and you will get this. So this is just an example to show the working of the Laplacian. Okay, now we go to the second part. I just thought of checking the time. Yeah. We will now go to the second part of the talk where I'm going to switch over to the Fourier transform. But if there are any questions at this stage, we can take the questions and then move to the. Otherwise, okay, I'll continue. Fine, I'll continue and questions can come at the end. Yeah, let's now go for the Fourier domain processing. Now, there are many transforms. I will mainly concentrate on discrete Fourier transform. But there are other transforms possible called discrete cosine transform. Okay. And there are other transforms also. But due to, because it's a 2-hour talk, I will do only discrete Fourier transform. Okay. What is a definition of discrete Fourier transform? And now the thing is, we define it like this. So what is f of x? Remember, f of x is the intensity value, and I have written it for the one-dimensional case. You can easily generalize this for 2D case. Remember, image is 2D. Right now, I'm taking it as a 1D object, and then the intensity value is multiplied by this complex exponential, and then you sum over all the pixels. Okay. And to calculate this, you have to choose a value of u. What is u? You can see that it will have dimension of 1 by length. See, let's say x is a distance, right? X is a distance. So this will be like 1 by distance. In other words, see, the problem for students is normally when they're introduced Fourier transform, they are taught in terms of time. You have a signal which is a function of time, and you take its Fourier transform, you get a function of omega, which is the angular frequency. But this is in terms of spatial coordinate x. And what is u? It is spatial frequency. So they have to understand this concept of spatial frequency, which is not so obvious because we are familiar with the frequency for a signal which is a function of time. But what is spatial frequency? Essentially, it means if you have an image in which there is a repetitive pattern, then that is it has got a particular spatial frequency, right? And then you divide by m. And one more thing I want to tell you is this definition of Fourier transform. It's not rigid. Different books use different definitions. Okay, so only thing is, if you define the forward transform, then the inverse transform gets fixed accordingly. So we should emphasize this because students may look at multiple books and they will see different definitions for Fourier transform. Then they will get confused. They will think something is right, something is wrong. But everything can be correct also because it's a matter of definition. I can define the Fourier transform in any way I want. I mean, the only thing is it should have this form. But what are the freedom available is I need not put this 2 pi factor, for example. Okay. I need not put this minus. If I don't put the minus here, the minus sign goes to the inverse transform. I need not even put this 1 by m factor. Then the 1 by m goes to the inverse Fourier transform. Or I can put 1 by root m in both. forward and Fourier transform. So there are multiple ways of defining the discrete Fourier transform. Okay, and this quantity, what you get is obviously a function of u, so it has to be calculated for different values of u going from 0 to m minus 1. Right? So if a 1D object has m pixels, then there are m spatial frequencies assigned. A numerical example later on, if you have time, that will clarify the meaning of this Fourier transform. Okay, we'll have a pictorial. And once, as I said, once I define this, the inverse Fourier transform gets fixed. Notice that if I put 1 by m here, there's no 1 by m over there. And if I have a minus sign here, there is no minus sign there. We can, in standard books, it is proved that if this is the forward transform, then this becomes the inverse transform. Basically, the for transform of the inverse transform. So what I mean is, I can take the f of u from here, substitute in the second equation, I should get f of x. That is a proof that it is a consistent definition, right? And here you are calculating as a function of u, here you are calculating as a function of x. Okay. But what are the properties of the DFT? There are many properties, but I'm mentioning the main important ones. Periodicity. So you can easily verify that if I replace u by u plus m, basically f of u plus m will be equal to f of u. Okay, this follows from the definition of the DFT. You can simply do this very straightforward, replace u by u plus m, then multiply it out, and remember that x is an integer, u is an integer, so this is simply 1. So I get back f of u, right? This is there. And the thing is, due to the periodic nature of the DFT, the Fourier spectrum may appear scrambled. Scrambled means mixed up. Okay, it is getting mixed up if we apply it directly on the image. I will show you an example, then it will be clear. For example, consider the Fourier spectrum of a 2D rectangular box function. Okay, so direct rectangular box function means there is a bright rectangle or even a square surrounded by a dark region, let's say. Okay. This is the 2D version of the 1D rectangular function. We know that if it's a 1D rectangular function and you take Fourier transform, you will get the sinc function, right? Sin x by x. But this looks very different. Why does this look different? Let us see. Yeah. So the actual thing which you expect is, if you have a rectangle like this, okay, the Fourier spectrum should look like this. This is called a centered Fourier spectrum. Centered Fourier spectrum means the zero frequency is occurring here. Okay. How do I get zero frequency? Simply put u is equal to 0. And remember, it's 2D version. So actually, I will have to generalize that whatever I said earlier. You will have a double summation, 1 over x and 1 summation over x and 1 summation over y. I'll do an example, then it will be clear. Okay, the 2D Fourier transform. But this is after centering. Okay. So let's look at how to center this. If you don't center, it will look like the previous slide. See, this is not centered. Why it's appearing like this is, remember that periodic nature is there. That means the zero frequency component is here. But then the frequency somewhere here is also close to 0. It's periodic, it's repeating. So you'll have to move this to that. Okay, for centering, you'll have to shift, you'll have to cut this up and shift things, unscramble them. That's what we say to get this. Of course, in MATLAB, there is a straightforward command which will do it's called FFT shift. You can do, and FFT is the fast Fourier transform. There is an inbuilt MATLAB function which will do the fast Fourier transform, and FFT shift will center the thing. FFT shift will do the Fourier transform and also center it. But for our understanding, how can you do? MATLAB will do it, but if you want to do it yourself or write a program to do it, what I mean is you can do it the following way. You can center the Fourier transform by multiplying the image by -1 for x plus y, where x and y are the spatial coordinates, before taking the Fourier transform. Okay, we can show that this centers the transform. How? From the definition of DFT, we have this. Okay, this is now the 2D. I have not shown 2D till now. You can see that this is a generalization of the 1D Fourier transform. Okay, instead of 1 by m, I have 1 by m into n. So it's a m cross n image. The summation over x, summation over y, that is summation over rows and summation over columns. Minus 1 power x plus y, f of x comma y. This is the pixel value. E power minus, so there is a complex exponential for u and x and a v and y. Then what I do, minus 1 can be written as e power, you can write it as e power pi jx, right? Remember, x is an integer. So e power pi jx is minus 1 power x, minus 1 power x. Okay, e power pi j is minus 1. So this will become minus 1 power x. So I can rewrite it like this. Then you combine these two. If you combine these two, you will get this. I got e power pi jx, and then if you multiply it out, you get it back, because e power 2 pi j into m by 2, and m cancels, 2 cancels, giving you, and minus minus becomes plus. So you will get back e power pi jx. So this will center, because now the zero frequency is shifted to m by 2, n by 2, which is the center of the region. So this will center the Fourier transform. So this is f of u minus m by 2, v minus n by 2. That means center has shifted to m by 2 comma n by 2. So the zero frequency component has been shifted to u minus m by 2, v minus n by 2. That means the transform has been centered. And the DC component, what is DC component? Zero frequency component. Zero frequency component lies in the center of the range from 0 to m minus 1, because zero frequency component is when u minus m by 2 is 0. That will happen if you put u is equal to m by 2. So zero frequency component has gone to m by 2, n by 2, which is the center of the wherever your plot, center of the Fourier domain, you can simply say. So zero frequency component has been shifted to the center. Okay, I'll skip this because we have already seen the 2D version of this. Now, significance of Fourier coefficients, some of which I already mentioned, but let me go through again. What is significance of Fourier transform? To get the significance, basically you can see that the zero frequency coefficient, zero frequency means what? F of 0, 0. Instead of u and v, I put 0, 0. I mean, instead of u, I put 0, instead of v, I put 0. So how to just go back to that definition of 2D Fourier transform. Sorry, 1 second. Yeah, I can take this, just ignore this minus 1 power x plus y, because that's not there in the original definition. You just put u is equal to 0, then you will get e power 0, which is 1. V is equal to 0, that's also 1. So this entire factor becomes 1. Then what I am doing is, this double summation means I am adding up all the intensity values and dividing by the number of pixels in the image. That means I am calculating average value. So f of 0, 0 is nothing but the average value. So the zero frequency component corresponds to the average gray level intensity of the image, which means higher frequencies correspond to sharp variations. They are not the zero frequency. Okay, so I'm just showing you the proof. I just for clarity, I have written it again. This is the definition of the 2D Fourier transform applicable to images. Just substitute u is equal to 0, v is equal to 0 here. What is going to happen? This exponential factors will become 1. So I will be left with f of x comma y only. Then I add up over all x and all y, which means I am adding up the intensity values of the entire image and dividing by the number of pixels. And this by definition is the average value of intensity of the entire image. Okay, now let's look at Fourier spectrum of typical images. Look at this image on the top. Let us say I've used MATLAB FFT function. This is what I see. Can we understand what's happening? Remember that the center of this is the zero frequency. So I am looking at the Fourier spectrum itself as an image. But you can ask one question. Remember, Fourier transform has the complex exponential, right? So it's actually a complex function. Okay, it's a complex function. So what are we plotting here? I am plotting only the magnitude or modulus of the complex number. So for each value of u and v, I am going to get a real part of the Fourier transform and imaginary part. I square the real imaginary part, take square root, and then plot it here. So you see that the zero frequency component is brightest. This is not accidental. In fact, for any image, zero frequency component will be the highest. This we can easily prove mathematically, but I will not do that. Just remember that the zero frequency component will be the highest. Okay. Essentially, this can be understood because, see, in the Fourier transform, what you are doing is you are adding simply some complex numbers, right? Because you have the e power 2 pi j ux by m and all that. That's a complex number. And when we add complex numbers, we can do it in the Argand diagram. So if you have zero frequency component, all the complex numbers are in the same direction. So they add up to give a large value. Whereas if there is a phase difference, then there will be different directions and the magnitude will be less. So that's why zero frequency component will always be bright. And then it will reduce as you go to higher. Remember, as you go to the edge of this image, you are going to see wherever it is bright. Zero frequency is bright means what? Zero frequency has a large magnitude. That's what it means. And as you go away from the center, that means you go to higher frequency, the value is becoming less. That's why it's looking dark. But of course, specific directions is looking bright. So what is the origin of this? In fact, you see that along this direction, it's very bright, right? And similarly along this direction. Now compare with the original image. This direction corresponds to this going like, start from the bottom right and go to the top left. What is happening to the intensity? You will cut across these edges which are there in the image, right? And remember, any edge is gives rise to a high frequency component. So that is why you are seeing, this means in this direction, high frequencies are present. Okay. Similarly, in this direction, high frequencies are present. That is this. And what about this? Where is this? This is also this is actually a defect in this. It's a damaged integrated circuit. This white thing is a damaged portion. And here also there will be high frequency component in this region. That's what is this. So the damage has given rise to this, whereas this and this are due to the edges, genuine edges which are present in the image. Fine. So now we have an intuitive feel for the Fourier spectrum of typical images. So I want to emphasize once again that main thing is the center will be bright and then the high frequency will be lower. This is true not only for DFT, even for DCT. You have something called the discrete cosine transform, where only difference is complex exponential is not there. It's a cosine function. But don't think it's the real part of DFT. DCT is not the real part of DFT. Definition itself is a bit different. But there also the zero frequency component has the highest value. Because otherwise, the cos will not be equal to 1, right? Cos is always less than 1. So for high frequency, it will be less than 1. And therefore, the higher frequency components are less than the zero frequency component. This kind of thing is also useful in compression because now the high frequencies are very low value. They are not that important. You can send the low frequencies up to some extent. Of course, in some directions, they are important. It's like I can cut out this part which is bright and then send it across. I can compress using this in the Fourier domain. In fact, JPEG uses Fourier compression in the Fourier domain. JPEG uses that. Okay, now a simple example will clarify. In fact, this example you can use in your class if you're doing, if you're teaching Fourier image processing and you want to want them to understand what is spatial frequency. Take this very simple numerical example, no complicated image like the previous thing. You have a simple image where how many pixels are there? Just it is 5, 5, 10, 15, 20, 25. There are only 25 pixels. And only non-zero pixels are in the middle. These are 5, 5, 5. Remaining all are 0. So just you have to substitute these. Your f of x comma y is this, these values. So most of the things in the summation are going to become 0. In fact, you can see that it is independent of y, right? It's not a function of y, it's only a function of x. So when you substitute, basically this value should be taken and substituted in that double summation which I showed you in the expression for DFT. If you do that, this is what you get. Okay. This 25 is because there are 25 pixels in the image. Okay. And then you have 5. So what happened to the summation over x? Remember that only for x is equal to, you have x equal to 3, right? X equal to 3, it is non-zero. Otherwise, it is 0. So that's what I have done here. When x equal to 3, 1 second, I think I have simplified it and then put it. Okay. When x equal to 3, you will have, otherwise, okay, I have to put 1 second. Okay, the convention I have used is a bit different. This is x equal to 0, not x equal to 3. I have taken x equal to 0 here, x equal to 1, x equal to 2. So when x equal to 2, it is non-zero. So that's how I am getting. If I put x equal to 2, x has disappeared and I'm getting 4 pi. 4 pi is basically 2 pi into x. X is equal to 2, so I'm getting 4 pi. So e power minus 4 pi ju by 5. And then the summation is over y. Okay. So we can easily show that if v is equal to 0, then the summation is equal to 5, else it is 0. Okay. This can be easily shown by treating these as complex numbers. Therefore, the Fourier transform of the image is as shown below. So you get 1, 1, 1, 1 here, and then rest are all zeros. Now, what does this correspond to? This nothing but corresponds to, so you see that in one direction, this is u direction. In u direction, there are high frequency components present. Remember, this is 0 frequency. This is 0, 0. And then as I go down, I'm going to higher frequency. So when you go to higher frequency along the u direction, you are having a high frequency. But in the other direction, there is no high frequency present. Now you look at the original image. If I go down, there is a high frequency present because I will cut across this edge. This is like an edge, right? If I go down, I'm cutting across the edge. So there will be high frequency. But if I go along y direction, it's uniform. So no high frequency in the y direction. There is only high frequency present in the x direction. And that is why the Fourier transform is also telling you there is high frequency along u direction. U corresponds to x, remember, and v corresponds to y. So there is high frequency present along the u direction and no high frequency corresponding to v direction, or you can call them x and y for clarity. Okay, one more important point when looking at these numbers is that students typically think there are 25 pixels in the original image and 25 values in the Fourier transform. So they will think one value here maps to that. No, that is completely wrong. Actually, each Fourier component has information about the entire image. Because if I give you this Fourier component, which is 0, 0, it has information about the average value of the image. And average value, remember, depends on the entire image. So that means each Fourier component has little bit information about the entire image. So there is no one-to-one mapping between those 25 pixels and these 25 values. This is one thing we have to make clear to students. You should not correlate one-to-one between the real domain and the Fourier domain. Fourier domain is completely different from the real domain. There's no one-to-one mapping. But in fact, it is a many-to-one mapping. All pixels in the image will determine what is the value of the zero frequency component. And for other components as well. So this is an important concept we have to emphasize, right? Because some understanding also has to be there. It's not just a question of using MATLAB to do image processing. You have to understand what happens when we take the Fourier transform. That is why I'm emphasizing on these numerical examples. Okay, now let's say we want to do frequency filtering in the Fourier domain, just like we did filtering in the Fourier domain. What are the various steps involved? First is, you take the Fourier transform, okay, and then apply the filter function. Normally, you will just multiply. See, remember in the spatial domain, you were actually what you were doing, I didn't use the word, but basically it's convolution. In the spatial domain, we take a mask and convolve with the image. In the Fourier domain, we just multiply. So convolution involves more operations than multiplication. Multiplication is each Fourier component is multiplied by the corresponding number in the filter function. So obviously number of operations are less. Then after multiplication with the Fourier function, we take inverse Fourier transform and get the enhanced image. Now, the confusion here could be, what about the operations involved in Fourier transform and inverse Fourier transform? Okay, I do less number of operations for the multiplication as compared to convolution. But what about the operations involved in taking Fourier transform and inverse Fourier transform? Actually, if you use fast Fourier transform algorithm, then the number of operations becomes less, and the total number of operations involved, you can show this by a detailed calculation, that the total number of operations involved is less than if you are doing in the Fourier domain. That's why this frequency domain is important. Frequency domain or Fourier domain is important because the number of operations involved is less when compared to the spatial domain. So this is a very important concept which has to be emphasized. Otherwise, students will think why we are unnecessarily doing all so many operations, forward transform, filtering, inverse transform, and all that. But the thing is, at the end of the day, the total number of operations is still less when compared to the normal spatial domain filtering. Okay. So what are the basic steps for filtering in the frequency domain? Okay. Multiply the input image by this factor to center the transform. Actually, if you are using MATLAB, don't have to do this. You can just use FFT shift, which will both take the FFT and it will shift it. Okay. Compute, I'm telling for general understanding because students may use some other language, then they have to know how to center the transform. Compute f of u comma b. Multiply f of u comma b by the filter function. What is filter function? If it's a low pass filter, then basically it will be 1 in some range. That is, for low frequencies, you will multiply by 1. For high frequency, you will multiply by 0. That is called the ideal low pass filter. We'll come to that. Different filter functions I'll just take up next. Multiply, compute the inverse DFT. Now, one more thing is there. You'll have to multiply because you'll have to undo what you did in the first step. So multiply by this. Okay. And obtain the real part of the result in, okay, not step 4, step 5. So what is this real part? Is, remember, after taking inverse Fourier transform, you should get a real function, right? Only real numbers should be there. Because remember, the Fourier transform is can generate complex numbers. But then when you take inverse Fourier transform and come back, you should have only real numbers. But what can happen is, remember, you are using a computer with finite precision. So many times there can be some small imaginary part which is completely spurious. Of course, if you are using MATLAB, it will simply ignore the imaginary part. That is also possible. But best thing for best results, you take the real part so that it doesn't give an error. Now, some examples of filtering. I talked about ideal low pass filter. I'll talk about a different filter called notch filter. What is a notch filter? You set the average to 0. That means the image is going to be very dark. This is the same image which I showed you some time back. But you see it has become very dark, but the edges are very sharp. Why that has happened is, you set the average to 0, but all other frequencies are preserved. That means high frequencies are preserved. If high frequencies are preserved, the edges will become very sharp. So that's why you are seeing very nice edges. And this is very good for recognition. For recognition purposes, contrast should be very high. The edges, basically, most recognition algorithms work on edge detection. So you have made the edges very prominent. So the edge detection algorithms will work very well now after applying the notch filter. Okay, I mentioned about low pass filtering. So the result of low pass filtering is similar to averaging. Okay, so that is what happens. This is a low pass filter. So here it is similar to averaging. It's getting blurred. That's what I want to say. So this is the filter function. If you want to understand the filter function, the ideal low pass filter is from a certain distance from the origin. That means origin means I'm talking about zero frequency component. Up to a certain radius from the zero frequency, filter function will have value 1 as shown here. Otherwise, it suddenly goes to 0. This is a representation of that. Bright means its value 1, dark means value 0. So it is bright up to some radius and 0 outside. Now what happens if you apply this on the image? Okay. This is a Fourier. So this is the original image. Then Fourier transform of this. Now these circles are not part of the Fourier transform actually. These circles are drawn artificially just to show that most of the information is in the innermost circle. Okay. Or most of the brightness, more precisely, most of the brightness is here. But you can ask one interesting question to students. What are these bright spots which you are seeing, which are also periodically spaced? This indicates some periodicity in the image. You can see that these periodic lines, remember that if I travel like this, I will see an impulse function periodically placed, right? And the Fourier transform of this periodic array is another periodic array. That's what it is. So these results are proved rigorously in textbooks where you take a periodic array of impulse functions, take the Fourier transform, you will get another periodic array of impulse functions. That's what you see. Okay. Of course, it's not only this. These lines, even this, if you go like this horizontally, you will come across all these edges of these rectangles, right? So they also give rise to this. But in the other direction, also you are having some high frequency components. Those are probably these edges. See, a high frequency component in this direction means there is a horizontal edge. There is a high frequency in this direction means there's a vertical edge. Basically, you get a high frequency when you traverse perpendicular to the edge. Right? Okay, so this is the effect of applying an ideal low pass filter. But you see one funny thing, it's getting blurred, that was expected. But you also see another effect called ringing. You see this, see carefully, you will see some circle kind of thing. There are many circles. Okay. So what happens is if you, okay, how to understand this? I will only give a qualitative argument to understand this. See, we said that we multiply in the Fourier domain. Multiply what? We multiply the Fourier transform of the image with the Fourier transform of the filter function, which is this, not the Fourier transform of the filter function, with the Fourier function. Sorry, with the filter function. So you multiply the Fourier transform of the image with the filter function. Filter function is defined in the Fourier domain anyway, so you don't have to take Fourier transform. It's already defined. But we know by convolution theorem that multiplication in the Fourier domain corresponds to convolution in the spatial domain. So you have to look at what is the Fourier transform of this, or Fourier represent, not Fourier transform, actually inverse Fourier transform, because you have to come to the spatial domain. So what is the representation of this filter in the spatial domain? That will come out to be actually concentric circles. You can easily show that it's some concentric circles. And those are the circles which you're seeing here. So you see here the circles. So what is happening is each point is convolved with the filter function, which is made up of many concentric circles. So at every point you get concentric circles. So that is the ringing effect which you're seeing. So how to get rid of this ringing effect? This is a problem because you are using ideal low pass filter. That is why we use something else called Butterworth filter. In order to avoid ringing, ideal low pass filter is not used. Other filters are used. There is something called Gaussian filter and Butterworth filter. Okay. So what is the logic for ringing to be absent? That means if you don't want ringing, the filter function should have a spatial representation which varies monotonically. This is not the case for ideal low pass. Remember, ideal low pass, I said there are rings. Rings means dark rings. So it's bright at the center and then dark, then again bright. So it is an oscillatory nature. Okay, it's like the sync function, you can say. Actually, there's a typo here. This should be monotonically. Okay, this monotonically varies monotonically. So this monotonic variation is there for Gaussian function and first order Butterworth filter, not for higher order. So what is Gaussian filter function? As the name implies, it's a Gaussian function. So the Gaussian filter is defined like this: e power minus d square by 2 sigma square. Sigma square is the variance of the filter. Okay. What is d square? D square is the distance from the distance of the frequency at u comma v from the origin. Distance square actually. So d square is distance square in the Fourier domain. Distance in the Fourier domain. Okay. We can show that the spatial representation of this will also be a Gaussian function. Fourier inverse Fourier transform of a Gaussian is a Gaussian. Okay, and forward Fourier transform also. So in the spatial domain also it's a Gaussian which varies monotonically. So if you convolve with the image, it will not give rise to rings. Same is the case with Butterworth function also. Butterworth low pass filter. This is what Butterworth looks like. So if it is n equal to 1, order 1, it looks like this. See, low pass filter means it should have maximum value for zero frequency. But ideal means it has a sharp change from 1 to 0. This we will change gradually. It's called Butterworth filter. Okay. And Butterworth filter, there is a particular expression. Let me see where I have it. Yeah, here. So this is the expression for, or the filter function for the Butterworth filter. It is 1 by 1 plus d by d naught. Remember, d is distance in the Fourier domain. Distance formula you use. How to calculate d? Use the distance formula. Okay. Root of u minus, remember from the zero frequency which is at m by 2, n by 2. So it will be u minus m by 2 whole square plus v minus n by 2 whole square. Add both, then take square root. That is a distance. Okay. D by d naught. D naught is some value which you fix. It's the radius of the filter. Then whole power 2n. N, if n equal to 1, it's called first order Butterworth. N equal to 2 means second order, like that. So this is the filter function. You can see that as d increases, this filter function value decreases, correct? Because in the denominator. So that is what you see from this figure also. It is going down because of it is defined as 1 by 1 plus d by d naught whole power 2n. And of course, the variation is sharper for higher orders. As you increase the power, the variation is sharper. Okay. So here d of u comma v is the distance from the center of the transform. D naught is the distance of the cutoff frequency. That's called cutoff frequency, where you want to cut off. In the case of ideal low pass, it's a sharp cutoff. Now, of course, it's not a sharp cutoff. And n is the order of the Butterworth filter. Sharper cutoffs are obtained with higher value of n, but at the cost of increase in ringing. See, if you see here, the fourth order Butterworth filter is almost like the ideal low pass filter. Very sharp change in the function value. So n equal to 4 is almost like the ideal low pass filter. So these are the spatial representation of the Butterworth low pass filter. So it's shown as a graph as well as an image. Okay, so you can see that this is monotonic. First order is monotonic; it's just decreasing, going to 0. Second order is developing some oscillation. The oscillation is becoming more and more as you go to higher order. The corresponding image also. These are the rings I was talking about. So in the spatial domain, so even for the ideal low pass filter, it looks somewhat like this. you will have rings, and when you convolve, basically at each point this is reproduced in the image. So you get all these rings in the image also after filtering. So if you don't want rings, which is obviously a fictitious feature, it's not good. So you should go for Gaussian or first order Butterworth. It will not have any ringing. Of course, some cases you might want high pass filter. Why do you need high pass filter? You want high pass filter to sharpen the images. Remember, low pass filter is for removing noise, and high pass filter is for making the edges prominent. Of course, it will also increase noise. So normally what is done is, first you apply a low pass filter, kill the noise, then you apply the high pass filter to sharpen the edges. So both are sometimes used. Both low pass and high pass are used on an image. Low pass to remove the noise, high pass to sharpen the edges. So high pass filters are used for sharpening edges. Ideal high pass filter, basically low frequencies are cut off. Okay. And of course, here also ringing is present because it's ideal high pass filter. IELPF means ideal low pass filter. Just like in the ideal low pass filter, you also have ringing in this case. And the expression for ideal high pass filter is very simple. Or for any low pass high pass filter, it's simple. You just take 1 minus the low pass filter. If you have the expression for the low pass, just do 1 minus that. You will get the expression for the high pass filter. Okay. Now I'll conclude by just talking briefly about the discrete cosine transform, because actually the Fourier transform is traditionally used, but nowadays it's replaced by many other. First it was replaced by discrete cosine transform. I mentioned about JPEG and all that. JPEG was using discrete cosine transform. Now, of course, you have even better things called wavelet transforms. So due to lack of time, I will not discuss, and maybe it will be discussed in some other lecture. Discrete cosine transform is what is used nowadays instead of DFT. Even though we teach DFT, many of the ideas carry over, but the advantage of discrete cosine transform is all things are real. There is no complex part here. Okay. Here I have used I and J, but those I and J are just instead of X and Y, I have used I and J. So the definition is a bit different. There is a factor of 4 and all that. This is the intensity value. Y of I comma J is the intensity value. Multiply by the cosine, another cosine factor. One for the X direction, one for the Y direction. Okay. So the main thing to note is, unlike DFT, DCT coefficients are always real. Whatever you get, these are called the DCT coefficient. The capital Y of K comma L. K comma L, K and L are the spatial frequencies, remember? Just like in the DFT case. But this is always real. The period of DCT is 4n instead of, okay? What happens is the second set of 2n are the same as the first 2n, except for a sign, negative sign, okay? So the thing is, why I am emphasizing this point is the Fourier transform. Suppose you take a, let's take 1D also, take an endpoint Fourier transform. There are n real coefficients and imaginary parts, right? So 2n numbers. Here also 2n numbers. Because the periodicity is 4n, but then the second 2n simply a sign change. We can prove these things simply by substitution directly. This last point can be proved simply by doing a substitution of the, you just take k and k plus 4n, you will get this result. You can show that the period is 4n. Okay. But the second set of 2n are simply the first set, except for a sign change. So independent numbers are only 2n. And the same 2n in the DFT also. Because why 2n there? N imaginary part and real part. So here also 2n DCT coefficients. Okay. So I have come to the end of my talk. We have 10 more minutes. So if there are any questions you can ask. So just for reference, most of the slides, as you can make out, I have taken from this very nice book on digital image processing by Gonzalez and Woods. It's the most widely used book all over the world. Okay, it has come to now 4th edition. It's become very fat, 1000 pages. If you look at older editions, they are 300 pages or 400 pages. But now with a lot of additional material, it has become 1000 pages. So it's useful for both teaching as well as research because it gives a lot of examples. It's also a basic book. mathematical level is not very high. There are other books, for example, there is a book by Jain, that's much higher level. Okay, for students it will be more difficult. So this book is widely used, and this is the first book which everybody should read if they want to understand image processing. Things are explained very simply with a lot of examples. Okay, and there are many other books. Some of the books are available online also. There is a site, given the link here. Okay, if you want, I can. One second, let me put this link in the chat box, because I don't know whether you can. May not be able to. Yeah, I have put the link in the chat box because it may not be visible. So if you go to that site, there are a lot of online books available. There, of course, it's called computer vision. It's the same as related to image processing. And I also have my own book as mentioned in the introduction. So, yeah. So that's all. Come to the end of this. I maybe went a bit fast because I ended before time. But if there are any questions, book is open access. No, sorry, book is not open access. It's actually ebook is also available. So normally it may be costly because it's a foreign publisher. Okay. So, but libraries, I think, can get access somewhat easily. Okay, for individual people, it may not be affordable. For libraries, okay, yeah, it is not open access. But there are other. I mentioned this site. So in that site, there are a lot of books available which are easily, you can access free of cost. So this site which I have put in the link in the chat box, that is free of cost. Yeah. So any other question?
Yeah, I request participants can ask the questions regarding the session.
Yeah, you can unmute and you can ask.
Yes.
Because I went it fast, some part, if it's not clear, we can go through again.
By yourself, you can unmute the mic and you can ask the questions here. So this is the interaction session. Now please go ahead.
Of course, one more thing I can do is I will send these slides across. I'll mail it, then it can be shared with participants. I think it's already done. I have already shared it.
Yes, yes, sir. Yes, sir.
Yeah, I already shared, so you can go through and.
Yeah, definitely we will circulate, sir.
Yeah, in case there are any questions later also, you can contact me. I'm putting my email ID in the chat box. So later, if you suddenly get some doubt or anything you want to share, you can send it to this email ID. I put my email ID in the chat box. Okay, you can contact me.
Yeah, participants, please interact with the speaker. So it is a golden opportunity for you. Sir is having a vast experience in image processing. And now you had a very good lecture now. Please interact.
Sir, good evening.
Yeah.
This is Mirza from Lord's Institute of Engineering and Technology, sir.
Yeah.
Sir, can you explain a little bit about scrambled Fourier transform?
Yeah. Let me go back. That part is. I think 1D case, the slide which I skipped, that may be first we can understand 1D. Okay, let me. Yeah. See, I think you understood that the Fourier transform DFT is periodic, right? From the
Yeah, sir.
Yeah. So what it means is it has a periodicity of m. So look at this figure now on top. So this is Fourier transform of some image, let us say. Okay, I have taken 1D case only. Let's say 1D image. So this dotted lines is the f of u. what is the meaning of periodicity? F of 0 will be equal to f of m. That's why the same thing, you see this peak, it's repeating after m points. Okay, and in between it is something else. Now what is happening is, so this, if you look at the value, suppose I look at m minus 1, value is m minus 1. You might think, remember this x-axis is u is what? Frequency.
Yes, sir.
So u is frequency, which means if I see a frequency like m minus 1, it looks like a high frequency. But actually it's not high frequency, because remember m is same as 0. Okay, so m minus 1 is actually like minus 1. So minus 1 is very close to DC, right? So m minus 1 is actually a low frequency. So number, numerically it will have a large value. See, suppose m is, let us say m is 256. Okay. Normally we take m to be a power of 2 so that the Fourier transform can be easily done. So if you take m to be 256, then this m minus 1 is 255. So f of 255, instead of u, you put 255. It looks like a large frequency, but actually no, it's not a large frequency. It's actually very close to the DC frequency, 0 frequency. Okay. So therefore, what is the problem if it is like this? The problem is, if I put a low pass filter, let's say I put a, remember I want to pass only frequencies which are very low, right? So how will I define a filter function? I will cut off very close to the 0, correct? But then I am also cutting off what is here, because that value is very far away. Understand? I will cut off what is at 255, but actually I should allow 255. See, what happens is you cannot, if it is like this is what is called scrambled. Scrambled means it is getting mixed up. What is the meaning of mixed up? A low frequency is appearing as a high frequency somewhere here.
Both low and high are getting mixed.
Mixed up, yes. From the number, you cannot tell whether it's low frequency or high frequency. That is what is scrambled means, mixed up. Okay, low and high are mixed up. Now, how to unmix it is, you center it. Center is means you have to shift the 0 frequency to the middle at m by 2. So it's like you just shift the whole diagram. So this peak which is at 0 is coming at m by 2. See, I shifted the peak from here to m by 2. That is the centering what I was talking about.
Shifting of the sequence, signal we are shifting.
Signal means in the Fourier domain. I am shifting in the Fourier domain, not in the real domain.
Okay, sir.
I am shifting the Fourier domain. This is, remember the x-axis is u. So I am shifting in the Fourier domain.
Okay, sir.
Okay. That means I am shifting after the Fourier transform. You can shift after the Fourier transform, or if you want to shift in the spatial domain, you have to do by that, multiply by that minus 1 power x. That's what I mentioned. Okay. But that looks complicated. I think for understanding, it's easier to understand shifting in the Fourier domain.
That minus 1 power, that one, no, sir?
Yeah, that one will basically do this. Okay. But as I said, that is just for understanding. In practice, what will happen is the shifting is done in Fourier domain. You have a MATLAB command for doing it. You don't have to, that is just for understanding purpose. I told minus 1 power x and all that. And 2D case, the 0 frequency is at a corner. So you have to shift the 0 frequency to the center. Here.
This is for 2-dimensional, sir?
Yeah, the bottom is 2-dimensional case. Top one is 1-dimensional.
Bottom.
Same thing. See, 2-dimension means what? Whatever you are doing in 1 dimension, do it in both directions.
Okay, sir.
So you shift it by m by 2 and m by 2 in the other direction also. So the 0 frequency will come to the center, this box which is shown. Okay. So here.
Sir, one more question in the chat box.
Yeah. Let me check. I wanted to ask a novel question of what is the best tool to use for image processing as compared to MATLAB. We have neural networks as well. See, when you say neural network, that is usually used for classification, things like that. It's a higher level thing. When you say image processing is a general term. Image processing may mean mostly improving the quality of images, filtering the image and all that. Neural network is generally used for a different purpose. Okay, and within MATLAB also you have, you can use neural networks. You can construct neural networks using MATLAB. It's not that these are two different things. Okay, is that clear? Nowadays, MATLAB has a lot of toolboxes. So there is a machine learning toolbox. Okay, you can check. I'll put it in the chat box in case you're missing out. You can check, machine learning toolbox of MATLAB. Okay, so this will have a lot of ready-made things which are used for classification. We have the same filtering tech in MATLAB as well. Yes, see all these for understanding purposes. We are teaching this ideal low-pass filter and we are multiplying and all that. So that is done for understanding purpose. In MATLAB, directly those filter functions are available. Okay, all the filter functions, ideal low-pass, Butterworth, directly it will be available. You just need to see what you can do is, as I said, MATLAB, a lot of help is there. You can read the documentation. In the help, you can search for filter function. You will get all the filter functions you want.
Yes, sir. Yes, sir.
And just a syntax you have to check. That's all. It's very simple. What is windowing? Windowing, okay. I think you are referring to the filtering, I guess, right? So, is that correct? Who asked this question? Windowing, yeah. Windowing is like, let's say, see, basically whatever is within the window, you want to allow that frequency. And whatever is outside, you don't want to allow. So let's go back to this low pass. 1 second, let me go to low pass. From that I can explain. Let's go to low pass. Yeah, here. See, basically you can think of this as a window. Of course, it's a circular window. So whatever is within this window, I will allow. What is within this window? From 0 frequency up to some distance I am allowing. Okay, this is actually some D0, you can say. This is D0. Up to distance D0 I am allowing. Whatever is outside I am not allowing. This is ideal low pass filter. You can also have high pass filter where you allow everything which is basically outside the window, and that's 1 minus this, and don't allow what is within this. So it depends on the purpose. If you want to remove noise, you apply low pass filter. If you want to sharpen the image, apply high pass filter. So depending on the application, you will do low pass or high pass. Okay, I hope I answered that question. Yeah.
So Thiru sir,
Yeah.
so can you throw a light on some of the latest research areas in image processing so that audience
Yeah.
can try in their level best?
Yeah. So as we said, there are different aspects to image processing. Okay. So in every aspect, there are recent research available. I'll go back 1 second. Let me go back. Okay, let me take one aspect which I mentioned long in the beginning. See this, for example, you take this. 1 second, there I missed it. Okay, you take that gray level transformation. I don't know, I'm not able to get the slide now. If you take the gray level transformation, here, gray level transformation. Here, I think I mentioned it. You have to choose, let us say you want to choose automatically. See, normally what happens manually in the, even if you write a program manually, you have to select this gamma, C and all that. So can we select gamma automatically depending on the image? So if it's a, as I said, if a dark image, you want to use, dark image means you want to use the gamma less than 1, bright image use gamma greater than 1, like that. Okay, this automating these kind of things is one aspect. And the other aspect is, a lot of research is going on now in, of course, a lot of it is already done, which is, let me go to that, here. The object recognition. So somebody was mentioning about neural networks. Okay, So a lot of work has already been done, but still that is not over. A lot of things are all possible in neural networks. See, one problem with using neural networks is people think directly they will take the image and give it to the neural network. You can do that, or you can first extract some features and then give those features as input. Okay. What is meant by feature is some particular thing, whether the image has edges present or not, horizontal edge, vertical edge. Like that, you can extract and then give it. So neural networks is one hot area. There are many such areas possible. One more recent development is, see, we teach I think in any ECE course, lot of signal processing is taught. Okay, and we start with Fourier transform. But as I mentioned, instead of DFT now DCT was used, and now the latest is wavelet transform. Okay, wavelet transform is very important. I don't know whether we are teaching that. That is what is currently used. Okay, because wavelets are more efficient when compared to Fourier transform. Okay, there is a lot of advantage. One thing is you can arrange it such that the entire computation uses integers. Okay, that is the advantage of wavelets. Here, what happens? You are doing some complex. Suppose you take Fourier transform. You have to multiply by that e power minus 2 pi j u x by m and all that, right? So that takes a lot of time. Whereas if you use wavelet transform, all that is not there. Okay, wavelets are defined in such a way to avoid all of those problems. So wavelets are very efficient, and that's the current thing. Different types of wavelets are used, and wavelets is also a very hot field. Okay, so that is one thing, but still research is possible in that. Or you can try for other new type of transforms. There are many other types of transforms. So one can come up with a new type of transform which is good for a specific purposes. So that is another area of research. What kind of transform is good? Okay, or can we come up with a new type of transform? So these are the current areas of research which are happening. Okay, there is a question. Image enhancement and improving resolution is same. No, the technical what I understand from resolution is in terms of number of pixels, right? When we say resolution of screen, that means we are specifying number of pixels. Image enhancement is not that. Usual understanding of enhancement is, of course, improving resolution will enhance the image. That is true. But enhancement can also mean improvement in contrast. So contrast and resolution are two different things. Okay, resolution means we are, I think, talking about spatial resolution. Whereas contrast is in terms of gray levels. Okay, so these two are slightly different. I hope that you got the difference. Resolution means basically, I think, number of pixels. Whereas enhancement means we are improving the contrast also. Of course, improving the resolution enhances the image. That is also there. See, enhancement is a very general term. It's improving the image. Improving, we can improve in different ways. Improving the resolution, but improving the contrast also. Both are enhancement. Yeah. So in short, enhancement is a broader term. Resolution is a particular term. Resolution means spatial, number of pixels. Enhancement is that plus other things like contrast. Yeah, both. That's what I said. Both improve quality, but in different ways, right? As I said, enhancement is a very general term. It includes many things. Resolution means you are basically increasing the number of pixels in the image. That is what is resolution. You say resolution of the camera is so many megapixel, right? When we talk about mobile camera, they will say it has so many megapixels. So that is a resolution. Whereas enhancement is that plus it may mean for a particular image, I want to improve the contrast, which is basically range of gray levels. How many dynamic range we call it, number of gray levels present. But both improve quality. Yeah, I think I have shared with professor. So they will, I think,
Yes, sir. It is with us. Definitely we'll circulate this PPT
Yeah, it
to
will be
the
circulated.
candidates.
Yeah,
No issue, sir.
yeah.
Any more queries, please? Hope there are no queries, sir. Vikram, sir.
Yeah.
I think people are hungry. It is now dinner
Yeah,
time.
it's late. It's late. Yeah, yeah.
Dinner
Yeah.
time. So as usual, even for last 3 days also,
Ah.
see, unfortunately, AICT has given this time, ATAL Academy, only
Ah.
7 to 9:30, 7 to 9 session and half an hour interaction.
Oh.
But the people are get vexed, it seems.
Yeah, it is difficult.
Anyway, our participants here for your information, they are participating even from Tamil Nadu, West Bengal, Maharashtra, Gujarat.
Oh, online.
Yeah, these states. Entire pan India. Okay, the
Oh,
people
it
are
is
there.
fully online. I thought it is physical.
No, sir. First week is online and second week is offline.
Oh, okay.
So thank you, sir, for your wonderful lecture. You have given very minute details. Okay, definitely the participants might have got benefited. Definitely they will use this knowledge to their students as well as for themselves. Definitely it is your lecture might have created an indelible mark in their teaching career and pedagogy.
Yeah, thank you, sir.
Yeah.
Thank you very much.
Yeah. So now I also thank the participants for your patient listening continuously for 2 hours. Even okay, in the 4th day also you all supported and cooperated for us. We expect the same cooperation even tomorrow also. Dr. Anil Kumar Uppala is coming from IIIT Hyderabad on time frequency analysis. Okay, it is also wonderful lecture. Okay, hope you all will attend sharp by 6:45, 6:50 p.m. itself, so that a resource person see that will not be waited for you. Right? Okay, I thank our convener and head of the department Rasool and my faculty members, all participants for making today's event is a grand success. Thank you all once again.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, Thiru, sir.
Yeah, thank you, sir.
Once
Yeah.
again.
You guys, thank you.
We'll conclude, sir.